to the like 5th session of this like journal cup thingy. Many more than expected again. And today, since we are a bit late, today we have Gianluca Pigeno. He's come here. Okay. Let people see your face. And he's a PhD student here at the University of Trento in the SML group led by Professor Passerini, and also in the knowledge management research group at the Fondazione Bruno Kessler, and is supervised by knowledge management group, and is supervised by Luciano Serafini. And today he will give us a presentation. He will talk about Neuro-Symbolic system to event recognition, and that's it, basically. Okay. Yes. And without further ado, I leave the stage to Gianluca.
Yeah, thank you.
And just an applause of encouragement, I would say.
Yeah, thank you, Giovanni, for the nice presentation.
I'm sorry, Gianluca. And if you have questions from the people at home, please write them into the chat, and we will forward them to Gianluca after the presentation. And enjoy.
Okay. Thank you, Giovanni, for the nice presentation. Hi, everyone. And in this presentation, I'm going to present a neuro-symbolic approach to structured event recognition that is a joint work with Andrea Passerini and Luciano Serafini. It was published.
Sorry, Gianluca, can you speak
louder?
Louder. Difficult.
It's difficult.
Okay. So as I was saying, it was presented at the 28th International Symposium on Temporal Representation and Reasoning. So I changed a bit the presentation. So I'm going to, before talking about the paper that we published, I'm going to give a small background in order that topic will be, I hope, understandable. So let's start with the background. So, okay, we can say that, as we know, so the goal of artificial intelligence is that of building a system that allow to simulate our cognitive process. And this scenario, we can make a distinction between symbolic versus a symbolic approach. Just a couple of words about this approach. So, symbolic approach was quite active between 50s and 80s, and are based on high-level symbols. So, it means that the idea is that usually humans, when reason about symbols, and so, for example, just to give you a short example, if I said to you, what is a strawberry? I think that all of us will have an image of a strawberry in our mind, and you recognize the strawberry since you recognize the color and the shape, and you can think that by connecting this kind of information, so we are able to recognize effectively the strawberry. So it's a sort of symbolic, we can say, reasoning. So if we look at the example of this kind of approach, we can find the logic programming, semantic net, and productions rule. And the pros of this kind of approach is that, as I said to you, it allows you to have explicit reasoning by reasoning about the knowledge that you have, and you can also derive, it's very easy to derive new knowledge that can be used in our scenario. And since usually this kind of approach are implementing from a logical point of view, they usually are interpretable. And the cons is that usually when you work with the symbolic reasoning and you try to model a scenario, you need expert knowledge. So it means that when you try to model to another scenario, you need knowledge coming from expert on that specific domain, and I think that it can be quite expensive. And these usually are approaches that are not robust to noise. And usually if you try to model complex scenario, you can have scalability issues as well. This is different from subsymbolic approach. So subsymbolic start, we can say, from 80s up to now. And they rely on the fact that we work on implicit representations, because here we don't need expert knowledge anymore, but we try to learn everything from data. So some examples include, as you know, Bayesian learning, neural network, and deep learning. And the pros are the following. So as I said to you before, is that you don't need anymore an expert, but you learn everything from data. And since you have usually use data, you are more robust to noise. And if you compare it with a symbolic approach, usually this kind of approach are more scalable. The cons is that, okay, the first one, I think that all of us know, usually these are black box model. And because we don't know what the neural network is actually learning. And usually are data angry approach. So you need that in order to learn to solve the task, you need a huge data set. And then you don't have an explicit reasoning capability that is a characteristic of symbolic approach. So as Queen Elizabeth said, we need a neuro-symbolic approach, not word. Okay. And so just a couple of words about neuro-symbolic approaches. So with neuro-symbolic approach, you try to integrate symbolic and subsymbolic approach. And just to mention some advantages of this kind of approach is that you can train using less data. You combine the low-level, you can say, processing coming from the neural network with an explicit high-level reasoning. And usually you are able to, since in this kind of approach, usually maybe you implemented the symbolic layer, maybe using some logical formula, you are able to constrain the predictions of the network in the forward step, but you can constrain the predictions in order to correct the low-level prediction of that is made from the network. And since you stack a symbolic layer on top of neural network predictions, these are interpretable model. Now, just to give some example, if you look at the literature, this integration has been made in different way. So in the first, so we have some approaches that are logic tensor network and lyrics that are approaches that work on fuzzy logic. So there you have a neural predicate. And the idea is that they don't work anymore with the standard Boolean logic, but they move to fuzzy logic, that is a relaxation of Boolean logic. So instead of having that a predicate can be true or false, here we have a predicate that has values from 0 in the range 0, 1. Then we can have some probabilistic graphical models, and here we talk about error potential. Such an example include deep structural models and deep logical models. And then we still have in the context when we talk about neural predicate, some approach that combine logic programming with probabilistic reasoning, and this include Neuro-ASP and deep problog that is going to be the topic of this presentation. So we'll give you very brief information about the background on deep problog. So, okay, so when we talk about deep problog, it's necessary to talk about prolog and problog as well. So when they rely on logic programming. So usually in logic programming, we work, so the main element are clauses, and clauses in logic programming can be factors that are unconditional true statement of both object and the relation, rules that can express relations among objects, and queries that represent interaction with the logic program. just to give a short example, so suppose that we have 2 coins, and maybe someone say, okay, the result of 2 coins, so they gives the 2 coins, one is head, and the other one is head as well. So these represent our facts, so our conditional true statement. Then we define a rule, and we say, okay, I have 2 head if both coin returns me head. So I can query this system, and the answer is in this simple example is true. So this is only a simple example. You can, if you look on the web, you can find more complicated example, just to give an intuition. And we can say that then we move to problem, and instead of having fact, here we have a probabilistic factor. So it means that now a factor has a probability attached to it, so probability between 0 and 1. And so now we are able to perform some sort of probabilistic reasoning. So now if I query the system and I ask what is query to add, in this example I will obtain the conjunctions of the 2 probabilistic facts, that in this case is 0.3. Now, suppose that I'm asking to self, okay, I want to move to deep problem. Okay, the idea is in deep problem is that you want to attach the so-called neural predicates. So you want to attach to logic programming neural capability, and you do so with the first row that you can see in the program, and where we declare a neural network. So this neural network gets as input an X, that is our input, and as an output, that is epsilon. And this epsilon has two output that are respectively head and tail. So now suppose that this neural predicate is a neural network that is trained, I don't know, maybe on images of coins in order to recognize head and tails. So for example, now I can do the same query, but instead here I have a neural network, 2 heads, that given 2 images will return me to the probability, okay? And this is a way, instead of, so the idea is that indeed we're using neural computations in this kind of approach. And so I have a logic layer combined with neural capability. This is a very simple example. So, okay, this was a really short introduction about the topic. So let's move to the actual topic of the presentation. So an application of Neuro-Symbolic Approach in the context of structured event recognition. So, okay, let me say that when we talk about events are structured entities because they involve different components. So in order to recognize a structured event, you have to recognize the entities that are involved in the event, their role, their relations. And for example, in these images, we can see that there is a guy that is preparing a cappuccino. In order to recognize that he's preparing cappuccino, I have to recognize that there is a person, and this person is a bartender, and he's keeping a pen, and he's putting the milk in the cup, and I have to recognize as well the cup. So the idea is that if you look at the literature, you can see that a lot of neural approaches in this kind of scenario usually have a limit or not having a support for background knowledge, so knowledge about the component that compose the structured event. And usually, if you try to solve this kind of task, you need a large amount of annotating training data. So it means that in order to train a neural network to solve this task, you have annotations at different levels. So you need annotations of the object, the position of the object, the role, and this kind of annotation. And okay, as I have already said to you, we can have a neuro-symbolic approach that has a support that provide us a support for the knowledge. So I can try to model this kind of structure and event by decomposing it. And the idea is that with this kind of approach, we are able to perform a training using what we call in the paper shallow annotation that we will see later, using a less amount of annotated training data. So, okay, the contribution of the paper are four. So first, we provide a formal definition of structured event recognition using the so-called shallow annotation. Then we develop a Neuro-Symbolic prototype using the propagate. Then we provide as well a framework to generate fully annotated videos. And we perform experiment by comparing a fully neural approach versus a deep problem approach. So, okay, let me define the problem. So first we have to introduce a first order languages. And these languages is composed by three sorts. We have O, that denote the object, T that denote event, and T the time points. When we have a constant of sort for denoting time points. When you have a binary relation that usually express a linear order between time points. Then we have two sets. The first one, that is P, is used in order to express the relations and the property of the object. And the second one is used instead to express event among these objects. Then we also have two predicates that are outcome and happens. So the first predicate is used to state that the outcome, so an event can produce, we can say an outcome. And the second predicate instead state that a certain event is happening between two time points. So using these languages, I can express, I can build this kind of formula. So for example, I can state that there is an object, and this and John leaves this object in a certain moment between time t1 on t2. Or I can say that the outcome of mixing milk and coffee produce a cappuccino. This is the formula, example of formulas that we can build using our defined language. So what is our name? Our aim consists from data sequences that we call D to generate an interpretations. In the paper we call it a narrative, that you can see a sort of descriptions or explanations of what happens in D. And the element of this kind of sequences can be, for example, vector, tensor, matrix. And just to give you an example, suppose that the sequences is a short clip showing a person that moves, leaves a bag, and then moves again. So what you want to do is that you want to recognize that in this clip, two objects are appearing, and then you want to recognize a set of facts. So you want to recognize that one of the objects is a person, the other object is a bag, and then you want to recognize the actions that the person is doing when he's doing that actions. And as I said to you before, we want to perform a sort of training using a kind of shallow annotation or partial supervision that consists in a subset of the events that happen or do not happen in the data sequence D. Okay, just to give you an example, suppose that now I define this kind of formula where I state there is a potential threat when a person moves with a bag, then leaves the bag, and then moves again. So the kind of the supervisions that I was talking to you before is that we will have videos of a certain length, and we will train our model using the supervisions on the structured event without directly providing supervisions on the low-level on the low level event composing, in this case, this kind of structured event. So in this example, I'm going to provide supervision about the fact that a potential threat is happening or a potential threat is not happening. Okay, in order to achieve this goal, we have to solve 3 tasks. So the first one is an object detection task. The second one is an object classifications and relation detection. And the third one is an event recognition. So in order to solve this kind of task, we introduced 2 neural networks. So we have first a network for detecting the object in the sequences. So this network will return as, for each object, a set of features. Then we will have a network for predicate evaluations that will take a tuple of features that refers to the object and will provide us a sort of probability value of that predicate happening in the data sequences. So for example, maybe we can have this kind of a network that the state, look, there is a person with a probability of, I don't know, 0.8. And okay, our goal is that we want to combine network outputs with background knowledge, and we develop a deep Roblox prototype for this kind of task. So, but before talking about the real stuff, as I said, we develop an event generation framework, and I want to talk about it. So, usually, if you look, as I said at the beginning, when you want to solve this kind of task, you need annotations at different level in order to evaluate your model. And then if you look at the different dataset, this annotation is usually not provided. And then usually this kind of dataset are manually curated and are not extensible. So if I want to introduce new event, is quite difficult. For this reason, we developed a mixed video generator. And this generator allows you to generate video with different length and different number of objects that in this case are mixed digit. And we define 2 types of events: simple event, where we have an object appearing, disappearing, entering, and exit, or structured event, and structured event where we have join add, join sub, and split that we will see later. And we generate a narrative, an annotations. So we will provide some information about the object, positions, the simple event, the structured event in which the object are involved, the name and the class as well. And okay, these are, wait, I'm lucky today that they are working. Okay, these are the example of the event that we created. So the first one is a join add. So we have 2 digits that moves around, and at a certain time they overlap, and the sum of the two digits appears. The only constraint here in the generations is that we will consider sums that are less or equal than 9. Then we have a join sub that is similar to join add, where we have 2 digits that moves and then overlaps, and instead of the sum we will have the subtractions of the 2 digits. And then we have the split where 2 digits that previously joined, then split and reappear again. Okay. For the experiment setting, we want to answer to this question. As a neuro-symbolic solution, an advantage is recognizing structured event with respect to a fully neural approach. And in order to answer to this question, we introduce 3 evaluation criteria. So we consider the correct classifications of the video, the correct classifications of the objects that are involved in the video, and the capability of the model to generalize to unseen outcomes, to outcomes for which we do not provide an explicit supervision. And okay, so we define. We create a scenario, and in our scenario we generate a video of 10 frames length, where we have two events, join add and join sub, where digit can appear anytime within the first half of the video, and only disappear if they join together. And the semantic is the same that we saw before. And then we have another event that is different, that we define with our framework, that is no join, when the two digits can stay fixed in the position, so one can move without joining. And okay, as I said, we want to provide supervisions that we call shallow annotation. So this is a kind of supervisions where we state the kind of structured event that is happening. So it is a join add or join sum, or it is not a join add and join sum. And we provide this as well as some supervisions about the result of the join. So because we have a structured event that is, for example, this is a join add 8, or this is a join add 7 on join sub. And okay, to do so, we create train, validation, and test it. So what we did, we took the means dataset when we use the user split in training, validation, and test to generate clips of this kind of event. In particular, for the training and validations, we consider outcome from 2 to 7. For join sub, instead, outcome from 0 to 7. And we generate as well video for non-join. For the test set, instead, we include the same of event of training and validations, but we include as well join add 8 and 9 and join sub 8 that were not included in the training set because we are interested in see how the model generalizes for this kind of example without having supervisions on that kind of example. So the event recognition approach that we use, I'm going to present the architecture that we use. So this is our detector. So our detector takes as input frames that are images that have shape 128 times 128, and this is passed to a network that is, if I remember correctly, this is a network with two convolution layers, each one followed by a max pooling layer, and we have two fully connected layers. And this network so takes as input the frame with the two digits and return this vector here. So where the two elements of the vector represent a sort of what we call in the paper visibility, that are value between 0 and 1 that indicates the presence of the digit in the frame. So if you obtain a value that is close to 0, so the digit is not present, close to 1, the digit is present. And then we have the other element. The first two indicate the presence of the first digit, and the second two elements indicate the presence of the second digit. And in this case, we return the top left coordinate of the bounding box, because MNIST have digits, if I remember correctly, shape 28 and 28. So since it's a fixed width and fixed height, we can easily reconstruct the bounding box by predicting only one coordinate of it. And then what we have is that we multiply the paths that we extract with the visibility digit in order to obtain the so-called soft patches. So it means that if you predict if this value will be close to 0, we will go we will obtain a digit that is an image of digit that will be completely black. And okay, this is after we get these soft patches, we pass them to another network that is performing classifications of the digits, and so we obtain. Okay, I noticed that there is a mistake on this. Okay, we predict a probability of distributions that state if the digit of the images, and we also provide another class in order to include the fact that a black patch is predicted, so there is no digit in the patch. So what we did is that we concatenate these two vectors with the vector that we obtain in the detection phase, and we pass to STM that is going to provide us a probability about the event, the structural event, join add, join sub, and join. And while for the predictions of the digit, we will gonna use the predictions of the last the classifier on the last frame. And this is the fully neural approach. Then, as I mentioned, so we develop a deep problem prototype. So as I did for the example of the coin, I introduce a neural predicate in which I'm going to define some input variables that is relating to the fact that I'm consider video and time, and I'm going to expect to predict digit. You can see the class 0 from 0 to 9 and -1 that is used in order to predict the absence of the digit. And then what I did is that, okay, I wrote some rules in order to state the conditions that lead to this kind of event. So I define a join add and a join sub, and as well as a no join. Okay, this is quite complex maybe to understand, so I will skip it. If you're interested, I can explain you later. Okay, some result. So what we did is that as I said we compared the classifications performed by the neural approach with the deep problem approach on the classifications of the structural event. We can see that this is the confusion matrix. Here you have the true label, and here you have the predicted label. And you can see that usually the network is able to recognize quite well the example for which the supervision is provided, but has some difficulties in understanding the semantic of the operation. So you can see that, for example, some example of join sub free are classified as join add free. While we can see that this is less evident with the deep problem approach. And another important thing is that if you look, the network is not able to recognize join add 8, join add 9, and join sub 8. So the network is not able to recognize event for which we didn't provide the supervisions. And while it's quite different for deep problem. So for the deep problem, you can see that indeed the network, so the deep problem, the neuro-symbolic approach is able to generalize to example for which we didn't provide exactly a specific supervisions. And this is possible by the fact that you are, for the background knowledge allow you to propagate knowledge in order to solve the underlying lower task that in this example here consists in the classifications of the digit. Indeed, if now we look at the result about the structural event, but we can say that is quite similar for the classifications of the digit, because now I can see that the deep problem approach is able to classify quite well the digit for which we provide the supervision. And this is possible because we state the supervision that we provide, if you remember, and is that we are going to state this is a structured event, and this structured event is a join add, for example, 7. So we have a supervisions of the digit. So we are able to learn this kind of digit, but we can also see that we are able with the decomposed approach to learn as well digit. In this case are 8 and 9, for which we didn't provide supervision. And okay, see, okay, just a short summary to wrap up all this stuff. So what we did is that in this in this paper, it was to present a neuro-symbolic approach based on the prologue for structured event recognitions. We perform a sort of end-to-end training with the so-called shallow annotation, and we compare it with a pure neural approach. And as I said to you, we see that usually a neuro-symbolic approach outperforms a fully neural approach, even if we are interested to see their ability in generalized we see that we compare these two approaches, and we saw that the prologue, when used a neuro-symbolic approach, this example is the prologue, it has the capability to generalize to unseen outcomes. And then we have some advantages in terms of explainability, because when you, as I said, when you stack a logic layer, you are able to reconstruct the step that led to you to a specific decision. And okay, this was only to wrap up all the stuff. And I think that I just finished the presentation. So.
Well, thank you, Gianluca, for the presentation. Okay. And like, there is some question from Zoom. I think it was faster than used. So let's see. So Tommaso said in slide 17.
17?
Yes. How could you explain the errors made by the prologue 17?
No, 17 su 19.
Okay.
How would you make? Okay, let's wait for the 17th.
Okay.
Exactly. Tommaso says, how could you explain the errors made by the prologue for the no join task? I can see many values outside of the diagonal, and the neural approach seems to perform better on the task. And maybe basically, I guess
this slide here, or
the previous slide.
Okay. Okay. I was thinking. Okay. Yeah, I think that is really depend on the rule that we write. So this kind of rule here, because we noticed that changing this rule after we published the paper, so we noticed that maybe changing a little bit this kind of rule, which actually reduces some error of no join. Okay, so it means that if we try to reformulate the rule in a way similar to the way we define the join add and join sub, we can try to mitigate these kind of errors. If I remember correctly. I've done an experiment a long time ago.
Makes sense.
Makes sense.
Okay. Okay.
They are satisfied. That's the word.
Yeah.
Stefano?
So I don't remember now the rule, but I'm sure that I have the rule.
Somewhere.
So Gianluca, thank you for the nice presentation. I have a couple of questions. The first one essentially elaborates on the one that you just received. And it's at the more general level, what kind of errors does this kind of model do? So have you had the chance to look at how does it fail in a sense? So you have the data, you have the rules, but you also have mistakes. What is happening there? In general, where do you expect it to fail? What are the big issues that you saw?
Okay. So in order to formulate this kind of scenario, we noticed that when you work with a neuro-symbolic approach with the problem, you can have some issue is if you try to consider maybe because now here we have a scenario with only 10 frames, but if you try to consider more than 10 frames, you can have that so the process is killed by the laptop. So because it requires a lot of memory, because I think that in order to answer the query, you have to build a circuit, okay, and the circuit can give some issue about the memory. So you can have not enough memory to answer a query that involve time, okay, even in this context. And this is why we select this kind of scenario. Indeed, indeed I'm working on temporal leasing, and I'm quite interested in finding a way to, I would say, to deal with the temporal dimensions in a tractable way. And I don't know if this one was one of the issues that I remember.
Yeah, thank you. I was more thinking in terms of prediction mistakes, common prediction mistakes.
Okay.
I'm just curious about that. That's why.
You mean that is relating to these plots?
In general.
Yeah, predictions. I don't know. You mean so about the deep problem? Or?
I mean, it's okay. I think that we can take this offline.
Okay. Yeah, you can.
The second question, though.
Okay, another question.
Yes.
I'm scared about your question.
The second question is, okay, so you mentioned explainability as one of the advantages of these models, which I agree with partly. But have you actually taken a look at the kind of explanations that are stood out of these kind of models? Meaning, have you when the model, I suppose that in this kind of data set is kind of, if the model detects a tree, then it is likely looking at the tree indication, right?
Okay.
But I would expect that in a data set where you have a lot of unbalance, for instance, you have a lot of trees but very few gates, maybe sometimes the method is over predicting a tree, but just by looking at the wrong thing, or the tree always appears with a 7. Then the next time only the 7 appears, and the method predicts 3
okay. So you mean, if I understand correctly, because we try to balance the data set by providing, you mean that you don't have the balance when you have the 2 digits. So because at the level because if you remember correctly, I created a data set, try to balance, okay, the structured event together with the simple event. So for example, I created, I don't remember, 100 videos of join add 8, 100 videos of join sub 7, 100 videos join sub 6. Okay, we can talk later. Are there any questions?
Any question from the audience?
Are you using the same neural network in both cases, right?
Yeah, thank you. I forgot to mention that. Okay, the network that you see here, this is a fully neural approach, but this network here is used here as well. And we use of that network the final layer, the layer that is this one here, the classification layer. So, but
yeah, so
in order to answer,
LSTM with the problem and practice.
No, because here you use the LSTM in order to predict the join add, or you have a probability distributions of the structured event. Okay, so the LSTM is used in order to provide the type of structure event happening in the clip, while here, so the decision is given by this predicate, and this predicate relied on these other one that are neural predicate. So you can see that we use this architecture here without this part here. Okay. And we only provide this.
Yeah, that was really the question.
Okay.
If you substitute the STM with
Okay.
the problem.
Yes, yes, exactly.
We have a question from Zoom. Paolo says, two questions. Is inference time with the Neuro-Symbolic approach comparable with respect to the Subsymbolic baseline? And do you envision any real-world application that could really benefit, readily benefit from this approach? Yes.
Yeah, indeed. Okay. Usually, inference time is quite expensive in this kind of approach, but I know that the guy working on the problem are doing some improvement. So I noticed that they published a paper some time ago. So maybe they reduced time in order to compute this. But yeah, indeed it was quite, if I remember correctly, it was quite expensive. As I said, the subsymbolic approach is really scalable when dealing with this kind of task. And indeed, I'm quite interested in order to make them more tractable, let's say.
And like the other question was like, do you envision any real-world application that could really benefit this approach?
I was trying to, because what led us was the ability, was showing that okay, we can try to solve this kind of task without having a complete supervision that is often done, you know, by applying pure neural, complete neural approach, you know. While in this kind of task, you can say, okay, I start from an higher level of supervision, then I have some background knowledge. So, for example, in that I show you before, you have you know the structural event, you know the decompositions of the structural event that you provide in terms of background knowledge, and you try to learn the decompositions with having directly supervisions on that kind of event. And as I showed you before, it's quite useful because we can generalize even for an example for which an explicit supervision is provided.
Okay.
Can I ask the last question? So it's just a general question. In these kind of approaches, is it ever possible that the model uses the expert advice only if the data is small? So when the data grows, it learns to trust the data more. So let's say if you are an idiot in some...
Okay. You mean if you increase the data set,
exactly. You learn to ignore the rules and you learn to trust the data.
Okay, we didn't perform this kind of experiment, but I think that if you increase the data set, maybe you can improve the classification of the ability of the network to recognize, for example, the digit, but the network will still not be able to recognize the digit for which you don't provide the supervision.
It's more for deep problem. So let's say I wrote the wrong rules for deep problem.
Okay, then your model fails.
But it didn't fail like asymptotically, like the data keeps coming, and will it still keep failing, or is there some way out of this as well?
Yeah, it's...
Okay.
Yeah.
That's
okay.
We have like another question from Zoom, from Tommaso, and asking, did you consider trying to use logic tensor networks for implementing this idea?
Yeah, indeed.
Because maybe they are more scalable than deep.
Okay. Yeah, here in this work we use deep problog because deep problog allows you to combine three fields, so neural network, logic, and probability. Yeah, indeed. Okay, logic tensor network is the work of my advisor. I think that maybe it will be scalable enough. So I think that we'll have some problem of scalability. And yes, but we can try. So indeed, we can. It would be interesting, I think, to because I noticed that usually some kind of neuro-symbolic. So the neuro-symbolic approach usually solve tasks that do not involve directly time. So maybe it will be interesting to have task. Maybe this one here, test with different frameworks and compare performance. You know, that can be quite useful, I think.
Yeah, but then, if you do with the logic tensor network, can you really do this when you do inference? I mean, when you do inference, you're not optimizing. So maybe it's a problematic too.
Okay. So, because now, okay, I have to think how to map this knowledge in logic tensor network. Yeah, if I'm honest, I have to think about it because I work on the deep problem part and not on the logic tensor network part. But yeah, I think that maybe can. So our initial idea after this work was trying to considering to map this kind of scenario in logic tensor network. Then, as always, we decide to move to other directions. So I don't know. Maybe in the future, if I'm still here, we can explore this.
Okay.
Thank you.
And well, just we get the last question, and then we call it a day.
What happens when you misclassify one digit? Are you trying to recover the right one by looking at the operation, or?
No, I think that when you misclassify the digit, they are considered a classification error. Okay, so you don't anything. So.
Another question. Does it ever happen that there are two errors in the two digits such that the final output is correct? I mean, they can happen, I suppose. Yeah, for example, if you predict 2 and 3, instead of 2 and 3, you predict 3 and 2, or you predict 8 minus 5 or whatever, minus 3. Yeah, you can interpret the 2 as an 8 and this as minus instead of a plus, for example.
Okay. So you mean, okay, if I understood the question. So you mean I recognize that this is, for example, a join at the 6, and I want to see that it actually classifies the 3 and the 3 of the. I don't remember. I think that we didn't check it, but I think that okay, because here we can only see that the network is learning, okay, to classify digits. Okay, but I think that we didn't check it. So yeah, it can be interesting.
Well, I suppose that as long as the hypothesis is satisfied.
Yes, I think.
Okay.
Hey, thanks.
Thank you very much for the presentation. And now we'll move, I guess, for a more like unstructured meeting in Povo. And for the people that are joining us in person here, like we'll move there in like 15 minutes. Yes. We meet outside Povo 1 in 15 minutes-ish. Then we go up to Povo to have a drink all together. And for the people from Zoom, thank you very much for attending, and see you next time.